Hello, welcome you all. So, in the last session, it is Module 1, Part 2 of Module 1, we had discussed the basics of thermodynamics. So, now today, uh, we are going to the Part 3 of the Module 1, that is internal combustion engine. So, in that, we are going to review on thermodynamics class. So we have already studied this thermodynamics in the basics of thermodynamics, these laws. So just to have, it will not take much of your time. So this will just have a review so that we can understand well the applied thermodynamics or power engineering. Okay. So in the thing is that in the last class we had discussed what are the properties, basic properties. You learned intensive, extensive property. Property is a point function, right? And there's an exact differential. And the other one is the property, that is heat, work, mass, heat, work, or energy, any type of energy. It's a path function. It depends upon the path. It does not depend upon the state at the point. So these things we have learned in the last class, and we have studied also. So what is the system? What is surrounding? And the interaction between the system and surroundings. So that is closed system, open system, and control volumes. So these are the things we are discussing. So now today, just we will go further in detail with the basic laws of thermodynamics. So the first law in the thermodynamics, it is the starting law. It is called a zero law, that is zeroth law of thermodynamics. So this zeroth law of thermodynamics, it is explains about the temperature. The concept of temperature is illustrated, or it is known by this Zeroth Law of Thermodynamics. It is the temperature. It is if you only we can sense it, isn't it? So we can say when you take our this one that with the skin, when we touch with our this one, so we will come to know it whether it is hot or cold, right? So it is the effect of the agitation of the molecules within that system because of the temperature. So there is an increase in the, when you add heat to a system, so there is an increase in the internal energy, and thereby the temperature of that system will increase. The density it reduces and the volume will expand. Okay, so that's how that temperature, with the increase in temperature, so this effect you are going to have that one, that is the bonding of the molecules will, it will lose out that bondings, and thereby it is this agitation of the molecules will start, and because of this internal friction we are going to get the temperature, right? So let us say if you want to know what is how that equilibrium of the temperature exists, so in that case it is explained by zeroth law of thermodynamics. In that we will take, let us say, we take the three bodies A, B, and C. Okay, A is in equilibrium with B. That means the temperature of A and B are same. And when A and B are in equilibrium with each other, if these two bodies comes in contact with the third body, that is C body, so after some time, again A, B and C all will become equilibrium with each other. So this is known as zeroth law of thermodynamics. It says that if two systems are in thermal equilibrium with the third system, they are also equilibrium with each other. So always we should explain this one in terms of applications. So because simply by having the definition, it is not useful to us. So if I take a thermometer, what is a thermometer? It is how many materials are there? That is a glass material is there, right? And the other one is inside the bulb. There is a mercury is there, right? So this mercury and glass, they are in equilibrium with each other. If we take this as a system, if A is a that is a pot or a glass pot, thermometer body, and B, let us say mercury, they are in equilibrium with each other with a third, whether it is an atmosphere or a bucket of hot water. You just put the thermometer in the bucket of water, hot water. After some time, you A, B, and the water, that is a third body is the water. So it becomes equilibrium, and then what we get is the temperature of the water inside. So then we are saying, see, this is the temperature. Say, let us say 40 degrees centigrade or 50 degrees centigrade is the degree Celsius of water temperature. Okay. So this concept, it is derived, the temperature concept, it is derived with the help of zeroth law of thermodynamics. Okay. So after this, we will go for the first law of thermodynamics. As this is about, it talks about the energy. It is the conservation of energy. That means energy is neither created nor destroyed. It transfers from one to the other. So this thing we have studied in the first law of thermodynamics. If a heat and work are the two types of energy, so either heat is transferred to work or work can be transferred into heat, complete. So any complete transformation of energy, it will be there always. If it not completes the transfer, some internal energy will be stored within the body, right? So let us say you take a closed system of a piston and cylinder arrangement. Okay. So in the cylinder, let us say that gas is entrapped already, and to that system, what I have done, just we are adding the heat to that. So when you add heat to that one, so it will expand, right? With the pressure surrounding on the piston is atmospheric pressure, right? So that is, we are keeping it at constant. So at that constant pressure, if we add heat to that system, so that system, it will expand, right? So that means when I add Q, the expansion of the gas takes place, and there you are going to have the pressure into the area of the piston, if you known to you. So then you can calculate the force into the distance, you can get, that is the energy work done, that is P into delta A into L, where A is the area and delta L is the displacement if it is there. So then P into A into delta L. A into delta L is nothing but the volume. So P into V, that is called flow work. As an expansion of the gas from initial control volume to the final control volume. So that means here the moving boundaries are there. The boundary is not constant. So there, that is complete transformation of, sometimes it occurs, but not all the time. So the Q can be converted to work, but if I use that work, it cannot be converted to heat. So that's that complete conversion. Say when I put it, the values, that is, if I put the work again, if I place that much of work, a pressure on the piston, if I put it and then it will come to its initial position, then you cannot get the same amount of heat transfer from the system to the surrounding. Okay, so this thing I can explain well with a board. So let us we will go for that. So here, as I said, uh, now we have to assume that this is a cylinder. Okay, this is the piston. So it is entrapped gas with this kind. So let us say a Q is added to this, heat transfer is added. So then if P is the inside pressure and if A is the area of the piston, so then P pressure into area is the force. This is the initial position, and let us say we have reached a final state at this point. Is delta L is the distance. So this piston is traveled because of heat addition. It is traveled A into L. So what you will get, P into V. So this is nothing but the flow work, right? So that means Q is transforms into the work done. Okay, small amount of Q you added and a small amount of work is done by the piston to the surrounding, right? Now if I want to reverse back this one, so add the same amount of work on this, that is force into the area. That is P into A is the force into delta L. If I apply it here, and again it comes to this initial position, we can bring it to the initial position. But at that time, so work is transforms into the system. Work is transformed into the system. And here we should get the same amount of Q, it should be rejected. So here this Q and this Q, they are not same. Because some energy, it is not available to transform into the heat, right? So that is called unavailable energy. So it is stored in the system. So that is W is dW is equal to du, it is dQ plus delta U. It is an internal energy. Or it may be like this, dQ is equal to du plus pdv, du plus pdv. That means pdv is what? It is a work done, right? du plus work done dw. So if there is a complete transformation, so in that case this will be 0. So usually this will not happen because some energy it will be stored within the system. So that is not available. So that is stored energy, it is known as internal energy. Are you getting it? So dq is equal to du plus dw, whereas this du is nothing but it is a cv into delta t, or it is cp into delta t. So what is cv and cp? It is a constant volume and this is constant pressure. Specific heat at constant pressure is cp, and specific heat at constant volume is nothing but cv. Okay, and then cp by cv, it is known as gamma. cp by cv, it is known as gamma. So this is the index of polytropic adiabatic process. So what we learned from the first law of thermodynamics is heat energy is equal to sum of internal energy plus the work done on the system. So after studying first law of thermodynamics, we will go for the second law of thermodynamics. It states that it is impossible for heat to flow from colder body to the warmer body without any work having been done to accomplish this flow. This is called Clausius statement. So actually it is a refrigeration process. In the refrigeration process, what you are doing, you are abstracting heat from the cold reservoir and you are feeding it to the outside. See, the temperature of the cold reservoir is less than the ambient temperature, right? So that is the temperature, and that temperature that heat you are abstracting from the cold reservoir, and that you are sending it to the atmosphere. That is a hot reservoir, right? So if it occurs spontaneously, that is without any work, so that is not at all, it is impossible. That means the heat can transfer from higher gradient to the lower gradient, right? It will not transfer. See, water cannot flow. Water can flow from the top at the higher elevation to the lowest elevation of that one. If there is a difference, potential energy is there, then only it will transfer. So this is against the nature. So against the nature means against the laws we are going at, right? These laws are have been brought with the help of the nature, So because generally what we are seeing from the nature, that from the mountain you can get the water source, right? From the elevation height of that one, it will come down. Whereas from lower region to the higher region, if you want to transfer that water to the highest position, so in that case we need to have a pump, etc. Right? So that you can take it as that is also a Clausius statement, right? It is impossible to transfer, that is to pump out water from the lower to the higher without any work done on the system. The same way, in the second law for the refrigerator, it is not possible for heat to flow from the colder body to a warmer body without any work having been done to accomplish this flow. This is called a Clausius statement. Okay. So here you can see all real refrigerators required to get heat flow from cold area to the warm area. So this is the work done on this one. So this work done plus QC is equal to QH. QH is the hot reservoir, the heat rejected. That QH must be equal to the work done plus QC. Okay. So we are not going to have this spontaneous flow from heat from cold area to the hot area without any work or compressor. Is it clear? So this is about the second law of Clausius statement. Now we will go for one more statement is there, that is called a Kelvin-Planck statement. So the second law of thermodynamics, Kelvin Planck statement. The Kelvin is a scientist, derived this one. So with a single source of thing, you are getting continuous supply, you are taking the heat and then getting the work. That is not possible. It is impossible to construct a machine which operates in a cycle whose sole effect is to convert heat into the equivalent amount of work. You are taking heat, complete heat, and then getting it to the work without sending anything heat to the other source. So the other source, that is heat and cold source, that is these two sources are necessary. So by taking by with a single reservoir it is not possible. So there must be two reservoirs. One is the hot and the other one is the cold source. So then you can transfer the work to the surrounding. Okay. So that is the perpetual, this is called a perpetual PMM1, that is a perpetual motion machine of a kind. So it is not possible to have build a machine which operates within a cycle whose sole effect is to take heat from a single source and it transforms into the work. So the second law of thermodynamics also it gives about the energy transformations. When you transfer the energy before and after the transformation of energy, so whatever you are getting, one is the usable energy after that and the other one is the unusable energy after that. So usable energy and unusable energy. So usable energy, it is called free energy. It can be get converted to the other one. Whereas unusable energy, it will not, we cannot get it, because so this unusable energy, it it see here the energy, if I take this block and this block, you take it as the same amount. So in that case the same amount you can get it, but the only the thing is that here this is unusable energy you are going to have this. So this energy, it will be stored in the universe, you know. So it is actually we are not going to get that energy, but that energy transforms. That is usually it will be stored at some place. So that thing, that is because of, it happens because of irreversible nature, right? So if anything, if it is an irreversible process takes place, so in that case you are going to have this more unusable energy after that. Okay. So this one, it goes to the this is the basic understanding of an entropy of a system where will always be greater than or equal to 0. So this entropy and the second law of thermodynamics, actually entropy is derived from the second law of thermodynamics. So the Clausius or Kelvin Planck statement, through that one we are going to get it. So this is a surrounding. The flask you take is a system. Okay. Now there are two types of reactions: exothermic reaction and endothermic reaction. Exothermic reaction is one in that heat is produced. If some reaction takes place, you are going to get the heat is produced during that reaction. Whereas endothermic, it takes heat from the surrounding. That is called endothermic. If a process is an exothermic reaction, it occurs in a flow. So in that case, delta H, there is a transfer of heat from the system to the surrounding. So heat is added to the surrounding. So that's why that entropy is a energy. Entropy is nothing but it is an energy. So that energy per degree Kelvin, that will also increase. So entropy, it is the heat transfer rate of heat transfer per unit Kelvin or per unit degree Celsius. Per unit Kelvin or per unit Celsius. That is usually we are taking K as Celsius and Kelvin as a in SI unit. So that's why we are taking Kelvin. So it is a dq by T. The ds is equal to dq upon T. If it is equal to dq upon T, so in that case, if it is heat is added to this one, there are so many reactions we are having, exothermic reactions. So in that heat is always produced and it goes to the surrounding. So there the entropy of the surrounding will go on increases. Okay. On the other hand, if it is an endothermic reaction is there, in this case, the entropy, that is the heat, it takes from the surrounding heat into the system. So that's why here the heat of the system will increase, whereas the heat of the surrounding, it decreases. So that means the abstraction of heat from the surrounding is there. So that's why there is a drop in the entropy is there in the surrounding. Here we can find there is a drop in the entropy, and in the exothermic we are finding the increase in the entropy. So try to understand. And so for reversible and irreversible process, what is the entropy of that one? Okay. So in the next thing, entropy of a gas. So I will not go in detail about this one, because if I explain these things once again to you, just I will take, this is a flask which contains an adiabatic valve having, this is the entrapped gas is there with certain weight is fixed. Okay. So entropy of gas, yes, is an entropy. It's an energy, it is kilojoule per Kelvin. The unit of entropy is kilojoule per Kelvin. Okay. T is the temperature, Q is the heat transfer. And the second law, what it says that the change in entropy is equal to dq upon T. The change in entropy before adding and after adding. So that is, if you take it, the change in entropy is equal to dq upon T. Differential second law, that is a ds. If I take this as a delta S, finite difference agar rahe. So if I take in the differential law, so in that case ds is equal to dq upon T, where H is the enthalpy. Enthalpy is nothing but H is equal to U plus PV. H is equal to U plus PV, and V is equal to, V is the volume and P is the pressure. So what you will get is dq is equal to dH minus VdP. So this thing, how you are going to get it, I will explain later on. So I think it is better I will take this session, this one, that is entropy of a gas, in the next part of our video. It is part 4, so that you can understand the concept of entropy of the gas, how it can be increased, and how we are going to get dq is equal to dH minus VdP, etc. Okay. So in the next session, we will go for the entropy and the entropy of a gas.